Slides are working
Yes.
all right, and I guess is the volume okay?
Yes, perfect.
Okay, great. Yeah, thanks a lot, everyone. Thanks to the organizers for the opportunity to speak here. It's always nice to be at HEFT, especially at this time, which is challenging for many people. So today, I'm very happy to tell you about our recent work on the effective field theory of dark matter direct detection with collective excitations. This is done in collaboration with my colleagues at Caltech, Tanner Trickle and Catherine Zurek. So to introduce the context for our EFT study, let me begin with a brief overview of dark matter direct detection, especially the efforts to get sensitivity to lower dark matter masses. So as we all know, the conventional searches for dark matter are mostly motivated by weakly interacting massive particles, and these are based on nuclear recoils. And this is a plot that we have all seen many times. This is already a little bit outdated now, but it still serves to illustrate the point, which is that despite the tremendous progress that we have made in probing the WIMP parameter space, we have not done a very good job at probing, say, sub-GeV dark matter, because all these curves, they lose sensitivity at around the GeV. And the reason is quite intuitive to understand. Suppose we have a dark matter particle that's about 100 GeV, and it hits a nucleus target, say a xenon nucleus, which has a very similar mass. And what happens is that we can try to detect a recoil signal. But if the dark matter is much lighter, say below GeV, then when it strikes a much heavier target nucleus, it will just bounce back, and the energy deposition is very suppressed, and that's why we cannot, or it's very challenging to detect a signal. But of course, a natural set of ideas to explore for sub-GeV dark matter is to use electron excitations. So basically, we start by realizing that in addition to the heavy nuclei, we also have the much lighter particles, the electrons in the target. So when the dark matter strikes a xenon atom, it can knock out an electron, and we can detect this ionization signal. A related set of ideas is to use semiconductors or other crystals with a band gap. So here, basically, instead of talking about individual atomic energy levels, we have to look at the crystal as a whole, where the electrons form band structures, and there are these valence bands that are filled or occupied in the ground state. And there's a band gap, which is typically order electron volts, and above that, there are conduction bands, which are empty. So when the dark matter comes in, by depositing of order electron volts energy, you can trigger a transition of an electron from a valence state to a conduction state. And then we can try to detect the associated ionization or scintillation signals. So this has been studied quite extensively in the past 10 years or so. And there are also experiments dedicated to searching for this, including Super CDMS, Sense, and DAMIC. So recall that the kinetic energy carried by the dark matter is about 10 to the minus 6 times the mass of the dark matter, just because the velocity is on the order 10 to the minus 3. By having sensitivity to order electron volts energy deposition, we can reach down to order MeV dark matter masses. So that's a lot of progress compared to what nuclear recoils can do. But still, we can keep asking the same question. What if we want to search for even lighter dark matter? So here, if the dark matter is lighter than about an MeV, it doesn't even carry enough energy to trigger this transition. So it just passes through the material, and we cannot detect anything. Well, unless we look at very small gap materials that actually people have looked into, like superconductors and Dirac materials. These are very small gap materials where the band gap is order millielectron volts. But these are somewhat futuristic in terms of experimental realization. So we would like to think about something that can be done in a more near term. So that's what motivated us to look into collective excitations. So the most familiar type of collective excitations is perhaps phonons and crystals. So these are sub-EV energy collective oscillation modes of the ions in the crystal. And the cartoon picture here is that when a dark matter comes in, instead of interacting with any single ion or electron, it can interact with the entire crystal and shake the crystal. And this is producing a phonon mode. So this is an idea that has been explored relatively recently, including by myself. And in fact, we have demonstrated in this work that the theoretical calculation that we have done for a wide variety of crystal targets show that we have pretty good sensitivity to the sub-GeV dark matter parameter space. And here I'm patching together our projected reach plot and the standard nuclear recoil plot just to see how much more of the parameter space we're sensitive to. And that's the theoretical part of the story. On the experimental side, there's also some very exciting news. There is a funded experimental project called Tesseract, which is based in Berkeley, that's ongoing. They're designing very low threshold transition edge sensors for single phonon detection. So hopefully we'll hear from them about the experimental results very soon. So related to this, we might also be interested to explore other types of collective excitations. So one example that we looked into are magnons. So these are collective spin excitations in magnetically ordered materials. And the cartoon here is that, so here I'm showing the specific case of a ferromagnet where in the ground state, all the ionic spins are aligned. When the dark matter comes in, if it interacts with these ionic spins, it can trigger a collective excitation modes of all these spins. So this is a spin wave, classically speaking, and the quanta are called magnons. So magnons are more futuristic, perhaps, when we think about application to detecting dark matter scattering compared to phonons, but it follows a very similar set of theoretical frameworks. So we did the calculation for this case as well. But I should mention at the same time that people have also been talking about magnons in the context of axion detection, and there's an ongoing experiment called Quarks, which although it's not really trying to detect single magnons, but it's using a similar set of ideas. So up to this point, the focus has been pretty much on a two-dimensional parameter space like this one. So this is the cross-section versus mass. The cross-section basically characterizes the interaction strength. But of course, the dark matter parameter space is more than that. And we can imagine at the very abstract level that there should be a third axis, which is what I call interaction type. So what I'm showing here is for a particular dark matter model where there is a heavy scalar mediator coupling to the nucleon number. And this is what corresponds to the canonical model for the spin-independent interaction considered in nuclear recoils. But of course, we can consider other models as well, and they live in different slices of this parameter space. And another often considered benchmark model is the dark photon mediator with kinetic mixing. And here we also did the calculation for a variety of candidate target materials, and the shapes of these curves look very different. So I don't really have time to discuss the interesting physics going on for what material does better than others, but I would refer you to our paper for a detailed discussion on that. But for now, just to motivate the introduction of using effective field theory, let me just mention that there are many more possibilities. And we can look at these slices of parameter space one by one, but that's really a lot of work. But so we want to do something more general. And in fact, when we think about theories of dark matter, it can quickly get out of control. There are just too many well-motivated possibilities. So we want to have a common description at low energy, and that's what brought us to the idea of using effective field theories. And in fact, the matching between many of these models onto the set of non-relativistic effective operators is already well known from previous studies on nuclear recoils. And here I'm just listing the set of operators. That's the first step of our EFT calculation. The second step is to start from these effective operators. And starting from this point, we can forget about the concrete models and just work with the effective operators. And the second step is to derive the dark matter couplings to the lattice degrees of freedom. And these are what we call the crystal responses. At the first order, so again, we can make an EFT expansion because we're only interested in the long wavelength modes. So here we can easily imagine that the end result will just depend on a few quantities at leading order. These include the particle number, how many protons, neutrons, and electrons that are contained in an ion in the lattice, and also the total spin, the orbital angular momentum, and spin orbit coupling. So these are the quantities that we expect to appear in this matching calculation, in this step of the matching calculation. And indeed, this is what we found from our results. And the final step is to use these crystal response functions in the detection rates calculation. So from here, we can calculate the phonon and magnon excitation rates. So importantly, phonons can in principle be excited via any of these responses because as long as the dark matter couples to something in the crystal, it can in principle shake the crystal to produce phonons. But magnons can only be produced under more restricted circumstances. So the ionic spins only come from the electrons, but not the nucleons. So it has to couple to the electron. And also in most cases, it has to involve the coupling to the spin of the electron. And in some more exotic cases, the coupling to the orbital angular momentum can also contribute. So that's basically the big picture of what we have done. And perhaps this has reminded you of something, which is the effective field theory of dark matter direct detection in the context of nuclear recoils. And this is a classic paper by Liam Fitzpatrick and others back in 2012, where they systematically generalized the calculation of nuclear recoils from just the spin independent and spin dependent benchmarks to the full set of EFT operators. And there the procedure is completely analogous, which is first to derive the non-relativistic effective operators and then compute nuclear responses in their case, and then compute the rates. So here, instead of the nuclear responses, we're interested in crystal responses because we're interested in the collective excitations in the crystal. But the overall frameworks are very similar. So if you're familiar with that story, it's worth keeping that in mind as we move through the rest of the talk. And also if you're interested, check out more details in our paper. So because I only have 20 minutes, this is not really not enough time to go into the technical details of all these calculations. So in the next few slides, I'll try to show you briefly using a set of examples of how the calculation goes, just to highlight a few important points of this calculation. So here I'm listing the set of operators again, but in this table, we put them into 4 categories depending on whether the operator couples to the charge or the spin on the standard model side. Charge in the broader sense, in that it can just represent a particle number, and also depending on whether the operator involved the relative velocity. So this classification is motivated by the fact that the operators in the same category induce the same crystal responses, as you can see from these red text over here. So the set of benchmark models that I'm going to focus on in this talk are dark photon mediator models. So on the standard model side, we have the coupling to the electromagnetic current, which can happen via kinetic mixing. On the dark matter side, there are several possibilities. The minimal possibility is that the dark matter is charged under this dark photon. And in this case, we have the standard spin independent interaction. characterized by the operator O1. But there are more possibilities. For example, the dark matter can couple via an electric dipole moment, and here is the dimension 5 operator in the relativistic theory. In the non-relativistic theory, we generate O11, so different operator. Similarly, we can consider a magnetic dipole dark matter model where 4 of these operators are generated at leading order, and they generate different crystal responses. And finally, we consider an anapole dark matter model, which is a dimension 6 operator in the relativistic theory. And here also operators in different categories are generated. So starting from these operators, we can then compute the crystal responses. And here, this formula is showing the general results with the contribution from each operator multiplied by their coefficient. So this is in terms of the effective scattering potential. And from this, we define these crystal responses highlighted in red. So from these, from the previous matching exercise, we can directly read off the terms relevant in this master formula. So for example, for these 2 models, we just pick out the C1 and C11 terms respectively. And we see both just involve the coupling to the particle number. And in this case, we say they only induce the end response, and this is probed by phonons, but not magnons. For the other 2 models, we see there are more terms generated, and they involve not only the end response, but also the S and L responses, which may induce magnon excitations as well. So I should mention I'm not going to show the rest of the calculation, but basically the idea is to quantize this effective scattering potential in terms of the lattice degrees of freedom, phonons and magnons, and that will involve some condensed matter details specific to the material we're looking at. But in the end, when we put everything together, we can compute these projected reach. So this is showing the phonon reach for kilogram year exposure, and assuming a background free experiment by default. This is the reach on the product of the couplings of the mediator to the dark matter and the electron versus the dark matter mass. And we can see that these 4 models that I just talked about, they exhibit a nice hierarchy, which can be simply understood from the EFT power counting. And for the targets, we considered both gallium arsenide, which is one of the materials already in use in the SPICE experiment, which is one of the sub-experiments for the Tesseract project that I talked about, the one in Berkeley. And the other is silicon dioxide, also known as alpha quartz. So this is also a well-studied material, and people know how to synthesize it, and it turns out to be one of the best targets that we found in the theoretical study. So this might be pushed forward in the near future as well. So we see that quartz generally does better than gallium arsenide as expected. Although I should mention that these targets do not have S or L order, which means that the phonon excitations can only proceed via the coupling to the particle number, but not the couplings to the spin or orbital angular momentum. But as I mentioned, 2 of these models also generate couplings to S and L, so we want to probe these responses as well, and these are best done by looking at magnons. So here I'm zooming in on these 2 models and overlay the phonon reach curves with the projected magnon reach curves, considering 2 targets. One is Zig, yttrium iron garnet, which is one of the best studied, perhaps I should say the best studied magnetic material. And it has S order, which means it can probe the dark matter coupling to the spins. And this is also the one used in the quarks experiment. And the other target, alpha ruthenium trichloride, is a more speculative one, but it has several nice features, including having both S and L order, so it can probe multiple responses, and also the gap magnons are at very low energy, so that explains why the reach curves extend to much lower masses. Overall, we see the magnon reach is a little bit better than the phonon reach, which is expected again from the EFT power counting analysis. But we see that actually by optimizing the phonon experiment, namely by using one of the best targets, silicon dioxide or quartz, we can get somewhat close to what we can do with magnons. So this is, I think, an encouraging piece of news because phonon experiments are definitely technically more mature. So with phonon experiments, we can already probe a lot of the parameter space for these well-motivated models. So I guess I'm running out of time. Take-home messages. First, collective excitations such as phonons and magnons offer a novel path to detect light dark matter. And on the experimental side, new experiments such as SPICE, which is part of Tesseract in Berkeley, are moving forward. And on the theoretical side, we have developed the EFT tools for computing direct detection rates for general dark matter models. So I'll stop here. Thank you very much for your attention.